Hello and welcome. Today, we're going to tackle a real classic from the world of kinematics. Yep, we are diving deep into problem 1.41 from one of the most famous physics problem books ever written. We're going to break it down step by step. All right, let's get into it. So if you're in physics or engineering, you've almost definitely heard whispers about this book, i.e. Irodov's Problems in General Physics. It is absolutely legendary for its tough problems that really truly test if you understand the core concepts. And today, we're taking on one of those challenges head on. And here it is, the beast itself, problem 1.41. So it's describing a point moving around in a plane. We're told its tangential acceleration is just a constant, a. And its normal acceleration grows with time, pretty fast actually, as t to the fourth power. And we know it starts from a dead stop. So what's our mission? We have to find two things, the radius of its curved path, which is r, and its total acceleration, w. And this is the big twist, we need to find them not in terms of time, but in terms of the distance it's traveled, s. So here's our game plan. First, we'll unpack what the problem actually gives us. Then, we'll do a quick refresher on what these different accelerations mean. After that, we'll build what I like to call the time-distance bridge. This is the key. And once we have that, we can solve for the radius and then the total acceleration. And finally, we'll step back and ask, what does all this math actually mean for the particle's journey? All right, first things first, let's just lay out all the clues and all the pieces the problem statement has given us to work with. Okay, let's break this down. We've got two parts to our acceleration. The tangential part, at, is just a constant, a. Simple enough. But the normal part, an, that one's changing. It's equal to bt fourth. We also know our starting point. At time 0, it's not moving. And our goal is crystal clear. Find r and an as functions of the distance s. Now, before we jump into any calculus, let's just make sure we're totally clear on what these two different kinds of acceleration are actually doing to our poor little particle. Okay, so think of tangential acceleration as the gas pedal acceleration. It pushes right along the path of motion. Its only job is to change the speed, to make the particle go faster or slower. In this problem, it's just a constant a, so our particle is just steadily speeding up. And then you've got normal acceleration. This is your steering wheel. It always points perpendicular to the velocity, pulling the particle towards the center of whatever curve it's making. It has zero effect on the speed. Its only job is to change direction, to make the path curve. So to put it super simply, tangential is all about how fast, and normal is all about which way. They're two totally separate parts of the motion, and to get the whole picture, you've got to understand both of them. Okay, now we get to the real heart of the problem. You see, we've been given everything in the language of time, t, but the final answer needs to be in the language of distance, s. So we have to build a mathematical bridge that connects t and s. We're going to start with what we know for sure. Tangential acceleration is just the rate of change of speed, right? So dv dt is equal to a. To get the velocity, we just integrate that with respect to time. That gives us v of t equals at plus some constant, c. But wait, the problem told us the particle starts at rest, so at t equals 0, v is also 0. That makes our constant c, well, it's just 0. So our speed at any time t is simply v equals at. Perfect. Next up, we use that velocity to find the distance. Velocity is the rate of change of distance, so ds over dt equals v, which we now know is at. Let's integrate again with respect to time. That gives us s equals 1/2 at squared plus another constant. And if we assume it starts at distance 0, that constant is also 0. And there's our equation for distance. And bam! This right here, this is our bridge. All we did was rearrange that distance equation. Now we have an expression for t squared that only depends on s. This little formula, t squared equals 2s over a, is the absolute key that's going to unlock the entire rest of the problem. It lets us get rid of t whenever we want. So, with our bridge built, we are finally ready to tackle the first part of the question. What is the radius of curvature, r, as a function of distance, s? So, you got to ask yourself, what's the physical connection here? How does a particle's speed and its turningness relate to the actual radius of its path? Turns out, there's a really fundamental equation in physics that ties all this stuff together. And here it is. The normal acceleration is equal to the speed squared divided by the radius of curvature. And this should feel right, you know? If you want to make a really sharp turn, a tiny r, or if you want to take a turn at a really high speed, a big v, you're going to need a much bigger normal acceleration to pull you in. Okay, let's just walk through this nice and slow. Step 1, we just rearrange the formula to solve for r. So r is v squared over wn. Step 2, we plug in what we know for v and wn in terms of time. A little bit of algebra there simplifies it down to a squared over bt squared. Now for step 3, this is the magic moment, we use our bridge. We swap out that t squared for 2s over a. And finally, step 4, we just clean up the algebra. And there it is, our first answer. The radius r is equal to a cubed divided by 2bs. Excellent. 1 down, 1 to go. Let's keep this momentum going and figure out how to calculate the total acceleration as a function of distance. Now remember, tangential and normal acceleration are just components. They're at right angles to each other, so you can think of them as the two legs of a right triangle. And the total acceleration? Well, that's just the hypotenuse. So to find its magnitude, we can just use the good old Pythagorean theorem. The game plan here is pretty much the same. It's all about substitution. First, we need to get Wt in terms of s. We know Wt is bt to the fourth, which is just b times t squared squared. So we use our bridge again and swap t squared for 2s over a. Boom. Now we have Wt in terms of s. We plug that expression and Wt equals a back into our Pythagorean formula. Now, it looks a little messy, but after you simplify the algebra and factor out an a, you're left with our final answer for the total acceleration. So we did it. We crunched the numbers, we found our equations, but what's the story here? What do these final results actually tell us about the physical path this little point is taking? Let's just look at what our results really mean. For the radius, r, notice that the distance, s, is in the denominator. That means as the particle travels farther and farther, its path gets tighter and tighter. It's spiraling inward. Now look at the total acceleration, w. The distance s is in the numerator, inside that square root. That means as it goes farther, its total acceleration gets bigger and bigger. So the big takeaway is pretty fascinating. This particle is constantly speeding up while also spiraling into an ever sharper turn. And that leaves us with one final thought to chew on. We found the total acceleration. But what about just that normal component, a sub n, the part that's responsible for all the turning? Based on everything we found today, what happens to just the turning acceleration as this particle goes on and on? Does it eventually level off? Or does it just keep growing forever? Something to think about. Thanks for joining me on this one.